Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. We are from Group 6, Section 4 under Dr. Amnani binti Shamsuddin. We will present about our project assignment flash distillation separator for ethane propane mixture. And this is our teammates, Kashfin, Wong Yan Chai, Siti Haja, and me, Zulkifli. First of all, we will talk about the introduction of this group project assignment. In this part, we will explain a little bit about flash distillation. This system is used to partially vaporize a liquid feed to separate it into vapor and liquid components based on its volatility differences. As you can see in this diagram, it shows how flash distillation works in a real system. First, we will heat the feed using steam in a preheater. Then, we drop the pressure through a valve which causes a part of the feed to vaporize instantly. In the flash vessel, vapor and liquid will separate. The lighter component goes out from the top as a vapor, and the heavier one will comes out from the bottom as a liquid. It is fast and energy efficient, perfect for separating mixture like ethane and propane. Moving on to the Raoult's law. Raoult's law describes the vapor-liquid equilibrium of the ideal solution. It states that a solvent's partial vapor pressure in a solution or mixture is equal or identical to the vapor pressure of the pure solvent multiplied by its mole fraction in the solution. It can be written as below. There you can see the top of the slide for the equation liquid phase, and the bottom is for the vapor phase. For the objective of the project assignment is to design a flash for ethane and propane mixture.
So next we will be moving on to process and composition conditions. So here's our overall process of this project. So first we will determine the temperature and pressure. So the temperature is based on the normal boiling point of ethane and propane, and we will take the middle point of it. And this also applies for pressure. Pressure, we will take the dew pressure and bubble pressure of ethane or propane, and we will take the middle point of it, which will be discussed after this. So next, after that, we will determine the overall composition, operating pressure and temperature. And after that, we will use Anton equation to calculate the pressure of the operating system. And last but not least, we will use Rod's law to determine the.
Now, proceed with the typical process condition part. Before the flash calculation, we need to assume the operating temperature and pressure. So now, we assume the operating temperature first. From table B1, the normal boiling point of ethane is negative 88.55 degrees Celsius, and the normal boiling point of propane is negative 42.05 degrees Celsius. Since the operating temperature need to be between the normal boiling point of ethane and also the normal boiling point for propane, so we assume the operating temperature is negative 65 degrees Celsius. For the operating pressure assumption, first we need to calculate the saturated pressure. From the reference for, the Anton equation is log 10 saturated pressure in millimeter of mercury equals to A minus B over C plus the temperature in degrees Celsius. So we subs all the parameters A, B, and C into the Anton equation, and we can get the saturated pressure of the ethane is 309.5489 kilopascal, and the saturated pressure for propane is 32.4071 kilopascal. Next is to find the bubble point pressure. At bubble point, y equals to 0 and x equal to 1, which means that the zi is equal to xi. The formula of the bubble point pressure is the sum of the xi times with the saturated pressure. So the bubble point pressure that we got is 170.978 kilopascal. Next, we find the dew point pressure. At dew point, x is 0 and y is 1, so the zi equals to yi. The dew point pressure equation is 1 over the sum of the yi divided by the saturated pressure. So we got 58.6718 kilopascal for the dew point pressure. Since the operating pressure need to be between the dew point pressure and the bubble point pressure, so we assume the operating pressure equals to 115 kilopascal. So we can conclude the typical process condition. First, the overall composition. The mole fraction of ethane is 0.5 and the mole fraction of propane is 0.5 because we take equal molar for both species. Next, the operating pressure is 115 kilopascal and the operating temperature is negative 65 degrees Celsius. Here are some assumptions. First, Reaction mixture is an ideal solution. Next, it is in steady state operation. Third, no heat loss to surrounding, and the fourth, Rhodes law is applied. So this is a simple process flow diagram that we draw to have a better understanding of our project.
Next is flash calculation. We need to calculate the K values for each component using Rod's law. According to the equation 13.16 from textbook, K value equal to vapor pressure of the pure component over operating pressure. We already calculate the vapor pressures and the operating temperature, and the operating pressure is 115 kilopascal. So for ethane, its vapor pressure is 309.5489 kilopascal, and when we divide that by 115, we get a K value of 2.6917. For propane, the vapor pressure is 32.4071 kilopascal. So dividing by 115 gives a K value of 0.2818. Next, we calculate the amount of vapor and liquid moles that will be formed during the flash process. This equation is based on the moles fraction and the K value we just calculated. Overall moles fraction has an equal mole fraction of 0.5 for both ethane and propane. Substitute all the values, we get the vapor amount V is 0.4006 mole. Since the total feed is 1 mole, the amount of liquid L is just 1 minus V, which equals 0.5994 mole. After finding V and L, we can calculate the vapor phase mole fractions using the equation 13.105 from textbook. So for ethane, substitute the numbers in, we get a mole fraction in the vapor phase of 0.8022 mole per mole. Then for propane, we can subtract ethane's mole fraction from 1. Lastly, we calculate the liquid phase mole fractions. For ethane, dividing 0.8022 by its K value of 2.6917 gives us 0.2980 mole per mole. Then for propane, we again subtract ethane's value from 1, giving us 0.7020 mole per mole.
So moving on to the next part, which is graphs. As you guys can see here, this is our PXY diagram of ethane and propane at negative 65 Celsius. So to construct this graph, firstly, we have to calculate the P1 set value and P2 set value using Antoine equation at negative 65 Celsius. As you guys can see here, the values are listed below to the left side here. And after that, we have to construct a table to the right side here, as you guys can see. And we start off with the pressure value at 32.4. And which affect the value of x1 is to be 0 because there is no liquid left at 32.4 pressure at negative 65 Celsius. And after that, we have to calculate the value of y1 using the pressure in the table and also the P1 set and P2 set values. And after that, we will use the value of P1 set and the pressure in the table to calculate the value of K1. The steps shown discussed earlier in our calculation sites. And after that, we have to calculate the value of x1 using the value of k1 and y1, which is also discussed in our previous section. So after doing all those until it reaches the pressure of P1 set, we get this graph. As you guys can see here, the y-axis starts at 30 and ends at roughly around 310. Next, here's our TXY diagram of ethane and propane at 101.325 kilopascals, which is 1 atm. So to construct this graph, firstly, we have to determine the normal boiling point of ethane and propane. As you guys can see here in the table, the value starts at negative 42.05. That is our normal boiling point of propane. And the value will end at negative 88.55 Celsius, which is our normal boiling point of ethane. So after determining that, we have to calculate the P1, the saturation pressure of ethane and propane at the given temperature in the table using Antoine equation. After that, we will use the X1, we will use pressure at 1 atm and P1 set, P2 set to calculate the value of X1. After that, we will calculate the value of K1 using P1 set and the pressure at 1 atm. And lastly, we will use the values of K1 and X1 to calculate the value of Y1. The steps are roughly similar to with what we did earlier, so we can apply that. Okay, so to conclude everything, this is what we have found based on our calculations we did earlier. So the operating pressure is 115 kilopascal and temperature is negative 65 Celsius. So we have also assumed the mixture is to be equimolar, so 0.5 mole of ethane and also 0.5 mole of propane. So as for the output, we have found out that there's roughly around 0.4 of mole of vapor and roughly around 0.6 mole of liquid. So as for the vapor mole fraction, there's roughly around 0.8 mole of ethane and roughly around 0.2 mole of propane. So for the liquid, 0.3 mole of ethane and 0.7 mole of propane. That's all. That is all from us. Thank you.